Today's lecture is on scientific notation. This is usually a little bit of a challenging lecture for our students, so just stick with me and you might need to watch this video again. Let's review for a second though. You already know what an exponent is. It's a number that tells us how many times a number should be multiplied by itself. In the example below, label the terms base and exponent. Well, we know the exponent is this tiny number up above here, so I'm going to write exponent here. And the base is the large number. This shows that the 4 should be multiplied 3 times by itself. 4 times 4 times 4, or 4 to the power of 3. And last time we learned some rules for how to work with exponents. Hopefully you remember a few of the rules from last time. Go ahead and pause the video here and write down any rules that you remember. All right, let's do a few of these examples together. Hopefully, perhaps you said that any number raised to the first power is that number. Let's give an example. 7 to the power of 1 would just be 7. Or maybe you wrote down that any number raised to the power of 0 is going to be 1. What if we have 8 to the power of 0? It would be 1. One of our other rules was that to multiply numbers with the same base, you're going to add the exponents. Let's say we have two numbers with the same base. Let's use the base of 2. Maybe 2 to the power of 3 times 2 to the power of 4. As long as the bases match, which they do here, all you have to do then is add the exponents. 3 plus 4 would be 7. Or perhaps you mentioned the rule that says to divide numbers with the same base, you can subtract the exponents. Let's use our base of 5, maybe 5 to the power of 4 divided by 5 to the power of 2. As long as the bases match, you keep the base, and then you can subtract the exponents. 4 minus 2 is 2. Good. Now today we're going to learn a fifth rule. This is a rule for working with negative exponents. It says a negative exponent in the numerator will get moved to the denominator and lose the negative sign. Okay, see our negative exponents here? This might look a little bit strange to you, so I think it's a little bit easier to understand the rule if we look at it. If we have a negative exponent, we're just going to put it in the form of a fraction. And you might be asking yourself, well, I don't really see a numerator or a denominator here. So remember that anytime you have a whole number, like 5, it's automatically going to be over a 1. You might not see it, it's invisible, but it is, it's over a 1. So this number here is the numerator. So a negative exponent in the numerator will get moved to the denominator. So make it into a fraction and get rid of the negative sign. So 1 over 5 squared would be 1 over 25. So a negative exponent in the numerator will result in a what? Fraction. Let's go to the next page now. Using negative exponents allows us to express small numbers that are less than 1. Now remember that just because the exponent is negative doesn't mean the answer is negative. All of these examples here with the negative exponent, those are positive numbers. So to see what I mean, let's plot these numbers on a number line. All right, if there's a negative exponent, we put it in the denominator and lose the negative sign. And I can rewrite that as 1, 2 to the power of 1 would be 2. Good. So our first one is 1/2. Now how can I plot that on a number line? I see 0, I see negative 1 and positive 1. So a half would be halfway between 0 and 1. There it is. And there's my first one. And my next one is 2 to the negative 2. 1 over 2, lose the negative sign, to the power of 2. Would be 2 times 2 is 4. So this one can be plotted at 1/4. And let's go ahead and keep the negative ones above it, just so we can get a good look. All right, 2 to the power of -3, 1 over 2, lose the negative sign, 3. That would be 2 times 2 times 2 would be 8. 1 over 8. So let's plot 1/8. If I have a quarter here, half of that would be 1/8. Okay, last one here. 1 over 2, lose the negative sign, keep the exponent, 2 to the power of 4. 2 times 2 is 4, times 2 is 8, times 2 is 16. 1/16. Okay, they're getting a little bit tiny here. There we go. Okay, you see that these are all larger than 0, which means that they are positive. None of my numbers were plotted in the negative sign of my number line. So just because we have a negative exponent doesn't mean the number is negative. In fact, the only way to make one of these numbers negative is to put a negative sign in front of it, like this. And this is how you'll see it. You'll see it in parentheses like that. And we can actually work this one out. Let's do that. Negative, and then in parentheses, this number here with a negative exponent is 1 over base of 2. Lose the negative sign, but keep the power, which would be negative 1 over 2 times 2 is 4. Negative 1/4. And that one actually would be plotted on the negative side of our number line, probably about right in here. One thing I wanted you to notice though, when you look at these here, this would have been 2 to the -4, what do you see happening to the exponent as I get closer to 0? As the number line gets smaller, the negative exponents get larger. So that's something to keep in mind. Negative exponents are very useful in the field of science, where numbers can be very small. For example, let's look at an atom. You might feel like you're back in either math or high school science here. An atom is the smallest particle of an element that can exist alone. The average size of an atom is only 0.0000003 centimeters across. You have to have a very powerful microscope to see an atom. And of course, this is not to scale, but if an atom was blown up, this is what you would see. An ordinary penny is made up of 20, oh wow, now this is a lot of zeros here. In fact, when I first wrote this down, I didn't even know how to say it. In English, we're used to pretty much stopping at either millions, billions, and even trillions, but keep on going here. What is this number? Well, I had to look it up, and this is 20 sextillion atoms. That's a large number with a lot of zeros. Next page. So can you see where I'm going here? There has to be a way to express very large and very small numbers, especially in the field of science. And luckily for us, there is. Scientists have developed a special way of writing very large and very small numbers, which is called scientific notation. In scientific notation, the number is written in two parts. First, you'll see a number that is less than 10. It must be one digit to the left of the decimal, and has to stay less than 10. For instance, 4.2 is a number less than 10. And next you'll see a power of 10, like 10 to the third power. In this case, 10 to the third power is really 10 three times. 10 times 10 times 10, which would be 1,000. So we're really multiplying 4.2 by 1,000, which would make it larger. And here's a hint for you as you're doing some of these. A quick shortcut is that you just move the decimal the same number of places as the exponent right here. Positive exponents like this one will make the number large, just as in this case we're multiplying it by a number with a lot of zeros here. Negative exponents, if this was a -3, are going to make our number very small, because remember, a negative exponent shows a fraction. Multiplying any number by a fraction would be small. Now let's go back then to the atom example. Express the number of atoms in a penny using scientific notation. So we need to start from a decimal, and this is the key for a lot of our students. They don't see a decimal and then they get confused. A decimal is at the end of a whole number here. So that is where our original decimal is. Okay, now I need to get one digit less than 10. I'm going to choose 2. You don't have to put 0.0, but I'm going to go ahead and do that. 2.0 times 10 to the what power? Well, how many times am I going to move this decimal to get it all the way to 2.0 over here? This one's a toughie. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. I had to move this 22 spaces to make 2.0 that large. But if you're a scientist, you would probably rather look at a number like this rather than a number with that many zeros. So let's practice writing a number that's very small this time. Remember we said that an atom is only 0.000000003 centimeters across? Let's express that tiny number in scientific notation using a negative exponent this time. So here it is in standard notation. Now we're going to write it in scientific notation, which will be some number times 10 to a power. We don't know what the power is going to be, but we do know that because this number is so tiny, it's going to have a negative exponent. All right, I can pick a number less than 10, and I see 3. I'm going to use 3, and I don't have to write 0.0, but I will. So to get my decimal all the way over here, to give me just 3, I have to move it 1, 2, 3, 4, 5, 6, 7. It looks like 8 times. And that's what the exponent always shows, how many times we moved the decimal. So 3.0 times 10 to the negative 8 is the same thing as this long number here. So I do hope that you notice the key difference here is that when we have a positive exponent, it was for a very large number, 20 sextillion. When we have a negative exponent, it represents a very small number. This number is, I don't know, maybe 3 millionths. It's very tiny. And I have a website here for you if you'd like to look at this on your own time. It's very interesting. It shows some examples of huge, huge numbers and then very, very tiny numbers. And it compares it to the size of a man. All right, the last page is practice. We'll practice these together, and then you'll have some homework as well. You should be able to look at a number in scientific notation and tell if it's a very large number or a very small number. So what we're going to do is just say large or small for each of these numbers. You don't need to write it, but I'm going to. 7.452 times 10 to the power of negative 7. Remember, this would be a fraction. Multiplying this number by a fraction would make it smaller. This is a small number. 8.09 times 10 to the power of 5. This would be multiplying 8 times a number with 5 zeros. That's going to make it quite a bit larger. Large. And 1.8 times 10 to the negative 5. Negative exponent represents a small number. All right, now I've given you some numbers in standard form, and I want you to write them in scientific notation. You can either pause here and do these yourself, or we can do them together. So first, I need to have a number that is less than 10, but it's got to have one digit plus my decimal. So 7 point, when you have numbers beyond that first digit, you have to include them. You have to show all non-zero numbers. So 7, 2, 0, 9. And even though this is 0, you have to include it because it's between some non-zero numbers. So 7.209 times 10 to the, first ask yourself, is it going to be positive or negative? 72 billion is a large number. You start from your decimal, and you have to go all the way over to here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 7.209 times 10 to the power of 10. All right, now this number is 3,459,000. That's a large number. I'm going to have a positive exponent here. I'm starting with my decimal here, moving it all the way left until I have one digit that's less than 10. 3 point, you have to keep these, 459. 3.459, and how many times do I move the digit, or the decimal, until it gets here? 1, 2, 3, 4, 5, 6. 3.459 times 10 to the power of 6. Now this time I have a tiny number, tenth, hundredth, thousandths, 509 thousandths, so very small. Your exponent this time is going to be negative. But I need to get it right here. And why do I have to get it just past the 5? Because 5 will be my digit less than 10, point, and you have to include what comes to the right until you get all of your numbers that are greater than 0 here. So 5.09 times 10 to the, how many spaces? 1, 2, 3. I had to move it 3 times 10 to the negative 3. Again, a very small number, so we know our exponent is going to be negative. I'm going to get it right here to 4.6 by moving it 1, 2, 3, 4, 5 spaces to the right. A lot of students do like to memorize, you go left when you want to do this, or you go right when you want to do that. That's fine. I'll put a shortcut for you on our Canvas site if you'd like to memorize that. But really, I like for our students to understand the concept. You need to look at the number and decide if it's very small, you're going to use the negative. Okay, so 8,405 is a fairly large number. In fact, if that was money, I think you'd say $8,405 was pretty large. So we are going to have a positive exponent, and our decimal will be right here. 8 will be our digit less than 10. Point, keep everything else until you get to non-zero numbers, 0.405. And how many times did I have to move my decimal? I don't see a decimal, so it's going to be at the end of my whole number. 1, 2, 3. 3 times. 8.405 times 10 to the third. All right, now we're going the opposite way. Write all of these numbers below as standard numbers this time. This is more like unraveling, right? So I've got 7.325 times 10 to the 8th. This is a lot of zeros. It would make my number here large, quite large actually. So we're going to have to move our decimal this way. If I moved it left, I would end up with 0.0000007325, a tiny number. It needs to be larger, so move it this way. Move it right. 8 spaces. 1, 2, 3, 4, 5, 6, 7, 8, and put your new decimal. I'm just going to fill in these gaps here with zeros. This 0 is just a placeholder. And I can rewrite that to make it a little bit neater. 7, 3, 2, 5. 5 zeros. And in English, every third, we put a comma there. Again, this one is going to be a large number. The exponent is positive. So 4.29. I'm going to move it 5 spaces this way to make it bigger. 1, 2, 3, 4, 5. Fill in with zeros. Rewrite if you want. There we go, 429,000. Now this time I have a negative exponent. That's going to make my 5.2 smaller. I'll have to move my decimal this way. 3 spaces. 1, 2, 3. And fill in with zeros. Rewrite 0.0052. Same thing, here's a negative exponent, and that's going to make my 7.03 much smaller. Move it 6 spaces. 1, 2, 3, 4, 5, 6. Put your decimal. Fill in with zeros just to hold the place. And you can rewrite 1, 2, 3, 4, 5 zeros. There we go. And last one here, again, negative exponent makes it smaller. So we're going to move to the left. Here's my decimal here, 4 spaces, 1, 2, 3, 4. There we go. Fill in with zeros, and you can rewrite. Okay, so you'll definitely want to make sure that you rewatch this video if you need to. I'm also going to provide you with a few other websites where you can watch other people explaining scientific notation, and please make sure that you do the homework assigned to this section. Now I'm going to show you a few minutes here of calculator hints. You're probably going to wonder why I didn't show you this at the beginning, but you do need to understand how scientific notation works. But there are a few little shortcuts that we can do, and I'm all about my calculator shortcuts. All right, let's take this large number here. When you have a very, very large number, like 72,090,000, how many zeros? Let me try that again. 72,090. 1, 2, 3, 1, 2, 3. There. When you have a very large number, you can just hit enter, and your calculator will say, you know what? Nah, I'd rather see it this way. And your calculator will go ahead and do that for you. Did we get it right? We did. 7.209 times 10 to the power of 10. However, look at this one here. Look at 8,405. If we follow the same procedure as before, I hit enter, your calculator says, yeah, I'm okay with 8,405. It's not too big. So I'm going to show you a special little button here, and some of you might remember this, might make it a little bit easier on the GED. Go up to mode, which is right there. Can you see that? Hit mode, and then you're going to use these arrows here to go down one level. Right now, I'm displaying my numbers in normal mode, which is standard. I'm going to go down over to hit SCI. That means scientific notation. Now hit enter. Now, all of the numbers that I input after I hit enter are going to be shown in scientific notation. So let's show 8,405. Remember before it said, okay, I'm fine with it. But now, there we go. 8.405 times 10 to the power of 3. Did we get it right? We did. So what I would recommend, I know you're thinking, that's really easy. I love calculator shortcuts. I'd recommend that you do them by hand to make sure you understand the process, but it's always good to double check yourself. Okay, and just to make sure, always go back up when you're done, and when it's flashing over norm, go ahead and hit enter, and that puts it back in the standard way for your calculator. Okay, so let's go the other way though. What if we have a number like 7.325 times 10 to the power of 8, and we want to express that in a standard form? What do? Well, there's another button I want to show you. I'm full of hints today. Times 10 to the power of n. This button here is what you're going to use for scientific notation. Let's try that. 7.325. Now hit your button here. There. Do you see how it went ahead and put times 10 to the what? Let's put 8. There it is. That matches exactly. 7.325 times 10 to the power of 8. Enter. And there you go. It's displaying it in standard form, or the calculator said it was normal. And is that right? 1, 2, 3, 4, 5 zeros. I believe that matches exactly what we have. Yes, it does. All right, so I hope these hints were helpful. And again, definitely make sure you do your practice for this section because it takes a little bit of time to get the hang of this. Thanks.